Let me start the recording, that way the folks who are not able to join us can catch up. So this question right here, I've gotten several questions about. So the way that I had intended that to be interpreted is that the G matrix containing the random intercept variance, that random intercept variance would be a positive number. The smallest that it could possibly be is indeed 0, but if that were the case, it would not be used, because you don't need a parameter that is 0 in your prediction model. So I intended for the random intercept to have a positive variance in answering that question. So if that helps resolve any ambiguity, I apologize for not being sufficiently clear. But since I have this up, does anyone else want to ask about anything? Otherwise, office hours after class as usual, if you want to talk one-on-one, or one-on-few, as it were. Then homework 2 is also available. There was a technical glitch after I put it up that it didn't look like it was available, but I fixed that earlier today, so that is ready for you. That is going to be due 2 weeks from today. Does that sound right? Checking. Yep, the 18th. So it was originally due on the 15th, but because I'm one class behind where I thought I would be at this point, it's the 18th. So you got 2 weeks to work on it. After today, you should be able to get started, and we'll see possibly, probably after Tuesday, you'll be able to do the whole thing. That's my expectation. So, all right. Any homework or logistical questions from anybody? No. Okay, then I want to remind you that you do have something due on Monday. Your second formative assessment is due. That's an icon under quizzes, just as a reminder. That is an opportunity for you to review. It's not something that you lose points for, so if you do it, you get your points, and we'll go over the answers together in class on Tuesday. All right then. So what were we talking about last time? I'll give you the beach as the background to dive into this. It feels like forever ago, doesn't it? It's only been a week. You know, like most normal graduate classes that meet once a week. To me, it just seems like it's too long to go without seeing everyone. I miss you too much. So what do you remember from last time? I'll take gestures, words, letters. No one remembers anything or wants to play? Does that mean we have to start over again? See, this is why I don't teach once a week. Running 3 different models at the same time, so adding a third pile of variance. Yeah, we started talking about a new kind of random something. The idea of measuring individual change through a combination of fixed and random effects. That was the new piece. So we're turning the corner from data focusing on just fluctuation over time into what is known as growth curve models describing individual change over time. And to do that, we do indeed need a third variance pile. So this is the picture we left off with. Does that sound right? Go back over this. So the idea here, terminology is everything. Fixed means everybody gets the same. A fixed effect is a constant. A random effect means everybody gets their own version. A random effect is a variable. So in this combination right here, the pictures are meant to illustrate all 4 possibilities in terms of whether an effect of time specifically, so the time variable on the x-axis in each of these pictures is there is a fixed effect or not, and there is a random effect or not. So the heavy black line in each of these is meant to convey the trajectory through the sample means, so what happens on average, whereas the individual lines are meant to be trajectories of different people. You would expect that each of these lines would not fit perfectly, like you'd see sort of, the residuals around it, but I didn't put those in the picture because I wanted to focus on just the main ideas. So this first picture here says there is no fixed effect of time because the average line is flat. On average, there is no change. There are no mean differences over time. So in ANOVA language, we would say there's no main effect of time. There is no random effect of time, no random slope for time, because everybody no changes the same. The average trajectory is a good fit for each individual. Parallel lines. Parallel lines also happen on the top right over here, but now there is a fixed slope for time. So fixed effect and fixed slope, by the way, are interchangeable. More generally, fixed effect is a higher order term because you can have an intercept or a slope, but I tend to slip in my language and say effect when I mean slope, so I'll try to say slope. Fixed slope on average because, yes, there is growth. So there would be, say, a mean effect of time. The means are increasing over time, but there's no random effect or no random slope for time because everybody's changing at the same rate. And these are the only two situations in the top two pictures here where a compound symmetry model for the variance would be plausible. Compound symmetry, quiz question, says that all the variances are the same over time and all the covariances are the same over time. The only way that that can happen is parallel lines. Everybody stays the same distance apart. So each of these two pictures has a random intercept. So my gesture that goes with this, the up and down hand, indicating differences on the y-axis. But those differences that were there at the beginning carry forward throughout the study. So you can think of it as mean differences for an individual as opposed to just initial differences. They're synonymous if everybody changes the same. And then down here, the other two pictures, they differ by showing what a random effect of time or a random slope for a time would do, in which everybody needs their own rate of change. So people change differently. They can either change differently around an average rate of time that is also positive or negative. So in the bottom right picture here, we have average change over time, but then the extent to which people show that change differs across people. Some people may not change at all. Some people may change a lot more than average. And then you could have an average that cancels out. So you could have no change on average because some people go up and some people go down. So you can have any four of these possibilities here in practice. So just because you don't have a fixed effect of time, for instance, doesn't mean game over, don't test for a random effect. But in terms of how you establish these things, there is a hierarchy because random effects are going to be phrased as deviations from a fixed effect, which means that if your effect needs to be random, fixed stays with it because they work together to combine to describe an individual's overall then value. So that's where we were starting. Okay, questions on any of that? All right, making sense so far? More or less? Big picture is what I'm going for right here. The idea of a fixed slope is the part that everybody gets. If everybody changes the same, that's all that's needed. A random slope is a deviation from the fixed slope for each individual that allows individual differences in change. So this random slope shown by the bottom two pictures here, that's the new part. That's the part that doesn't get specified within repeated measures analysis of variance. And you can see that if people change differently, what that implies is that the variance has to change over time too. So a compound symmetry model would not fit for these data. We would need to do something else instead.
Can I ask, I still don't understand why the two bottom ones are different with the left one being no fixed, the right one being yes fixed.
The no fixed is because on average, so the mean
On
trajectory
average,
here, there
okay.
is no change. Yes. So fixed refers to the average trajectory or the sample means for time for the outcome. You can think of it either way. And so it is possible to say there are no mean differences over time on average, but still have individuals differ in how they change over time. Question. So before, all we were doing is random intercepts. Yes. So starting at a different point, but the slopes remain parallel because we didn't specify anything aside from a random intercept. If you are talking about a compound symmetry model in which you only have a random intercept and no other random effects, that is true. That implies a prediction of parallel change. That's compound symmetry. The multivariate version, though, of the repeated measures ANOVA, the unstructured model, is much more general. It doesn't say that there are individual differences in change, and it doesn't say that there isn't. It lets all of the variances and covariances be estimated separately, whether or not that's necessary. So one of the reasons why each occasion might need its own variance is because of random slopes for time. And if that's the case, what we're going to see here behind the scenes is that allowing a random slope actually then creates a predicted change in the variance across occasions, such that you don't have to let each occasion have its own variance anymore. The random slope does that for you. So it's going to imply another pattern for what the total overall variances and covariances across occasions could be. It's a pattern that's being predicted when we add a random time slope. Okay, does that answer the question? Or other questions? Yes, I think so. All right. So then what does this look like in terms of models? So what I have are equations that map onto each of these pictures. This one, no fixed, no random, yes fixed, no random, and then a third for either of these combinations, because so long as you have a random effect, you have to keep a fixed effect with it. So picking up then on slide 11, hopefully my mouse will work today. There we go. So this is corresponding to the top right picture. So before we had an empty model that had no effects of time whatsoever. Introduce that using our new sort of multi-level modeling notation. Now we're starting to add fixed effects. So just to recall, the way that this works is that we are predicting an outcome that is in a stacked data set, meaning there is one column and it's one row per occasion per person. So even though you might think of this as like 5 variables, because it's 5 occasions worth of data, it's in one column. So from the perspective of the model notation and from the perspective of the program, it's just y. But it's y as the outcome per t for time point per individual. So t is the level 1 identifier, I is the level 2 identifier. So we had beta 0I before. Now this is not in red or blue. So I'm using red to denote parameters that are part of the model for the means, and I'm using blue to denote parameters that are part of the model for the variance. Beta 0I and its new friend beta 1I are neither, because they're not parameters. They are placeholders. They're like suitcases that hold estimated parameters. So beta 0I conceptually is how each person is going to get their own intercept. So beta 0I is the individual intercept. Likewise, because it's being multiplied by time, beta 1I is how each person is going to get a time slope. So note that time here, this is what's known as a level 1 predictor, because time is a time varying predictor. The TI on the time here means something very specific. It means that each person could potentially have their own set of time values. So time is just a column. It doesn't have to be 1, 2, 3, 4. It doesn't have to be the same for everybody. It can just be whatever it is. So then if we take these betas, which are how each individual gets their own version of an intercept and a time slope, they then become the equations at level 2. So the rule is every beta at level 1 translates into its own equation at level 2. So there's 2 level 2 equations now because I've got 2 betas to unpack. The first beta, 0, is the intercept. It gets unpacked the same way as in the empty model. It has a fixed effect and a random effect. So in this case, the fixed effect is this gamma 00 thing. That is the average intercept for the sample. Because of my predictor, this is no longer the mean over time. The definition of an intercept, no matter which class you're taking from me, I just talked about this morning or earlier today, the intercept is always the expected outcome when your predictors are 0. Always. In this context, when the predictor is 0 is when we're talking about time 0. You can put 0 at any occasion that you want. It could be the first occasion, it could be the middle occasion, it could be the end. The first occasion is probably the most common, and that's the one that I typically do most often. So time is already centered such that 0 is the first occasion. That way I can refer to my intercept as the predicted outcome at time 0, which would be initially. So the predicted intercept on average is given by gamma 0, 0. The deviation of each individual from it is given by the random intercept, the U0. So the random intercept U0 is how far off each person's intercept is from the average, which is given by the fixed effect. So the fixed effect is the middle, and then U is the deviation that gets you to where you are. That's why if you want to have a random effect, you got to have a fixed effect too, because the random effect is always phrased as how far off you are from something else. So this combination right here gives each person their own predicted starting point for their trajectory over time. And we don't necessarily care about what each individual U0 value is. All we care about is their variability across people. So we're not adding a U per person. We are adding one term that is the variance across people in the U's. So the random intercept variance is at level 2, represents between person differences in the intercept, represents cross-sectional differences, represents inter-individual differences, and the U0 variance is going to live in the G matrix. Okay. With me so far? Okay, now over here, this looks sort of silly. What do you mean beta 1 is just gamma 1O? Like, then why do I need both of them? Yes, because eventually we will have some more stuff here. But when you first add a fixed effect, then how each person gets their own time slope is just this one constant that applies to everybody. So in this model, which is called a fixed linear time random intercept model, that terminology is used to describe that only the intercept is random at this point. The slope is fixed. So how each person gets their own slope is one number, which means everybody actually does get the same. And you can see that more directly if you substitute in what each of these betas stand for back into the level 1 equation. The composite model at the bottom here, the term in parentheses here, that's my individual intercept beta 0, and then beta 1 is just this fixed slope right here, gamma 1O. And the numbers, by the way, the first subscript indexes which beta in the level 1 equation it goes with. So this is gamma O because it's talking about beta O. This is gamma 1 because it's talking about beta 1. The second subscript indexes the order within the level 2 equation. And just like we start counting at 0 here, we start counting at 0 here. So the first fixed effect in predicting beta 0 is the 0. The first fixed effect in predicting beta 1 has a 0 here as well. So this equation would result in this picture right here. That is what the model predicts. It allows a fixed slope. It does not allow individual differences in the slope. To get to those, we got to get down here. All right. Yeah, look, I had more animation. All right. So, in talking about what predictors are supposed to do in these models, every predictor that you add to the model, where you're adding a fixed effect for it in the model for the means, has a job to do. Just like in regular old linear regression, the job of a predictor is to explain outcome variance. The tricky part in these models is which one. So in this slide, how many different kinds of variance do I have right now? This is a finger question. Or a typing question, your choice. How many kinds of variance do I have? How many piles do I have? How many variance components do I have? 2. Yes, 2 indeed. I have E, which is sigma squared E. Those are the individual deviations around the line. And so now the line is predicted by each person having their own intercept but a common slope. I also have U0. The variance across people in the U0s is the variance across people in the intercepts. And given that everybody's expected to change the same, that intercept is constant over time. So I have within person level 1 E variance that lives in the R matrix, and I have between person level 2 random intercept variance that lives in the G matrix. I now have a fixed effect of time right here. Which one of these is it going to explain? Which source of variability should be reduced because I added an effect of time, a fixed effect on average? That's the tricky part in these models, is figuring that out. You got a 50-50 shot though. Want to make a guess? We got one guess for between. Anyone want to guess within? One guess for within. Okay, a few more guesses for within. The answer is it depends. However, in this context where everybody has the same set of time occasions or close to it, so people start the study like at the same time 0, it's within. Another way of saying it is E is level 1 variance over time. Time contains time level variance. Time is a time varying predictor, a level 1 predictor. Level 1 predictors reduce E variance. Level 2 predictors reduce U variance. So one question we might ask right off the bat is, okay, how much variance did we reduce? So to be able to answer that question, welcome to a measure of effect size for fixed effects within multi-level models, longitudinal models in particular, known as Pseudo R Square. Is this a term anyone's heard before? A few people? Pseudo R Square is used to refer to R squares that are not really R squares, but we want to treat them that way. And pseudo is not me being funny, that's what they're called. I didn't make that up. Like R square-ish. So that happens, say, in logistic regression, where the variability of the residuals is 3.29 no matter what, but we still somehow come up with R squares. It happens in this context. What pseudo R square refers to is the proportion reduction in each particular variance component. So you have as many pseudo R squares as you have piles of variance to be explained. And the formula for it, there's a couple different versions, but here's the one that I usually show. It's whatever the variance was before you put the predictor in, minus what it is now, divided by what it was. So the variance should be bigger beforehand, minus whatever's left, and then that becomes a proportion if you divide by what you had in the first place. So pseudo R square is a proportion reduction in variance as a result of adding a fixed effect. Now, why I say it depends which one gets explained is whether or not there's variance in the time predictor that is between persons. So that's an advanced topic, that's covered in chapter 10, but that can happen anytime you have what's known as an accelerated longitudinal design or a cohort sequential design. I'm trying to think of any other terminology, but it happens in practice if people start out at different points in time and you measure them longitudinally. So if I have a sample, say, of 80 to 100-year-olds, let's say I'm studying older adults at the beginning of the study, and I measure each of them for up to 8 years. Then time is both a between-person variable because people started off at different ages, and a within-person variable because they grew older as the study progressed. So in that case, just putting in time as age would explain both residual variance and random intercept variance simultaneously. In that situation, just having one effect for what is actually two variables is wrong. It's the cardinal sin of multi-level modeling, something that I call a smushed effect, and it is so unfortunately common. So we'll talk more about that later. But in the situation in which time is purely a within-person variable, which happens when people are all at the same point at time 0, then time should only explain level 1 residual variance. Okay. All right, does that make sense? If I have a time level 1 predictor, it should explain time level 1 E variance. If I have a person level 2 predictor, it should explain level 2 random intercept variance instead. So the predictor that it's measured at for that level explains the corresponding variance at that level. Okay. Yes or no? Maybe? Maybe it gets better as you see more examples of it. I think that will help. But here's something crazy that's going to happen, and I want you to be prepared for it. When you look at what happens to the estimated variance for the U-zeros before you put time in versus after, it's going to go up. And you didn't do anything wrong. And that's another reason why these things are called pseudo R squares, is because they can go negative. You can end up with more unexplained variance than you started with after adding a predictor. That can happen. It's often a sign of model misspecification, but not in this case. So I wanted to prepare you for what happens in terms of adding in a level 1 predictor such as time that's purely within persons. It's going to cause the level 2 variance to increase. So here's how it works. When we talk about what is between person variance in the random intercepts, or the idea of person mean differences, the number that the model comes up with as how big those differences are has actually been corrected for how much of that variation is expected just based on chance. So like if I assigned you all into breakout rooms, don't worry, I'm not going to do that because this isn't that kind of class. But if I assigned all of you into breakout rooms and I asked you to calculate, say, I did it randomly, let's say, and I asked you to calculate your mean age and report back to the group, would each of the breakout rooms have the same mean age of the people in it? Like exactly the same. Like this room has an average of 27 years old, and this room has an average of 27 years old, and this room has an average of... No, that's not going to happen. Not exactly. Now, if I randomly assigned you to the breakout rooms, though, then there should be no expected difference. So I can use sort of the observed difference as like a correction factor for what would have happened by chance. That's what this is doing for us behind the scenes in estimating the variance of the random intercepts across persons. It's subtracting out a correction factor for how much of that is just expected due to chance that would have been there even if there were no differences. And the way that it indicates that, the correction factor, is the residual variance divided by the number of occasions. So what happens is that the observed actual differences between persons and their means is broken apart into what the model thinks is true and what the model thinks is just random noise that would have been there anyway. And it subtracts off the latter to try and give you an estimate of what is true. So then this math is what causes the random intercept variance to increase at level 2, even though it should have stayed the same. So here's a numeric example to show you how this works. So let's say that in a data set, such as the one that was used in chapter 5 that we're going to look at in the example, the observed variance of the person means is 4.65. So if I calculated a mean across time for each person, I plug that into a variable and I get the variance of that variable, it's 4.65. And let's say that in a given model that's empty, the residual variance is initially estimated at 7.06, and there's 4 occasions. So then SAS is like, okay, cool, I can work with this. So let's take the observed variance, let's subtract off the part that's supposed to be due to just noise, and now you get 2.88. And the 2.88 is the number that pops up on your output. Okay, fine. So I have 2.88 as my level 2 variance. I have 7.06, and I could take those two numbers and come up with an intra-class correlation. which would be 2.88 divided by the sum of those two. Cool. Then if I add a fixed linear time slope, if time is purely within persons, if everybody has the same time occasions, starts out at the same point, then time as a level 1 within person predictor should only explain level 1 residual variance. So let's say that it does, and the level 1 residual variance goes from 706 to 2.17. If I plug those numbers into my pseudo R square formula, what it was, the 7, minus what it is now that's left, the 2, and divide by the 7, that works out to an R square of 0.69. So like 70% of what we were calling within person variability is just due to which occasion it was. That explains 70% of the residual. So then the new residual variance that's much reduced gets plugged into the correction formula, and the same between person mean differences were there to begin with. The net result is an increase. So now it looks like there's more between person variance in the intercepts than there was before, because there's less within person variance being corrected off of it. So that means this is what happens. It's a byproduct of estimation. You didn't do anything wrong. It doesn't mean your model is wrong. It is what happens. So I want you to be prepared for it. In such cases, in trying to describe an effect size for the fixed effective time, I would only talk about how much of the level 1 residual variance that fixed effective time has captured, because that's what's relevant here. This, by the way, is also why when people have advice about when you need a multi-level model versus when you don't, that conversation is rarely occurs for longitudinal data, but it frequently occurs for clustered data. So like if you see rules like, well, if you have an ICC of less than 0.05, then you don't have to do a multi-level model or shit like that. No, because this happens. It may start out with only 5% between person differences, and that's not a lot, so let's not worry about it, between group differences in that case. But after you put in level 1 predictors, it goes up. So the conditional interclass correlation, because of this correction factor, can be much, much higher, which is particularly when it's a problem, because then the effects of your predictors are going to be, the inference for them is going to be wrong if you don't have that intercept variance in the model. So this is one of the reasons why it is never safe to use just a generic cutoff as to when you get to care about having nested samples. This can bite you if you're not ready for it. But you're going to be ready for it because I just told you about it. So what's going to happen is that when we add fixed time into the model, the residual variance at level 1 goes down, which is going to make the random intercept variance at level 2 go up. All right, questions or comments? All right. So what's going on behind the scenes? What does this model right here say about your data? What does it say about the reason for person's dependency? What does it say under the hood about the predicted variance and covariance across time? This is what I want to tell you about. Well, at this point, the only thing that's random in our model is the intercept. We have not added a random slope yet. So what we are saying is this combination right here. We have a random intercept whose variance lives in the level 2 G matrix. We have an E, which this model so far says has the same variance across time with no covariance whatsoever. That's the sort of standard default for what R looks like in these models. You can change it, but not in every software program. So another way of talking about this is that R at level 1, the variance of the level 1 E's, represents the conditional version of the model because it's what's left after factoring in any fixed effects and any random effects. So after we control for the random intercept, people are supposed to be independent, occasions are supposed to be independent, and occasions are supposed to have constant variance. So when you put these two things back together again, you end up with this structure right here, compound symmetry in the V matrix, which is the marginal covariance structure. So a random intercept only says there's only one reason why the occasions from the same person were correlated, because of mean differences, and that's it. If that's true, then the variance should be the same across time also. That's what this model is saying if you only have a random intercept model. It is a parallel lines compound symmetry model. So here's some math that makes that point. This is in the book. If you want to have me walk it through line by line, I don't want to waste our time doing that here. But if you fill out the model and then work out what the model predicts for the variance to be at any one occasion, it works out to be partly level 2 random intercepts, partly level 1 residuals. Covariance at any pair of occasions A and B works out to be just the random intercept. Okay, cool. Then you get something that looks like this, which I also wanted you to be prepared for, because you will see it written this way in books and journal articles, and I want you to not go, like that, because it looks scarier than it is. So these are the mixed model equations that you will see if you took this class over in the statistics department, or if you used other textbooks that are written from that perspective. They will describe this same model as a series of matrices. So we have the y's for a given individual, the x's for a given individual, a matrix of constants, which means that there's no I on here, another matrix of z for the individual, another matrix u for the individual, and another matrix e for the individual. So this y sub I here is matrix language for one person's outcome. That is what is being described here. And if you go into the contents of the matrices, then you get something that looks a little more familiar to what we've been doing. Okay, I've got in this case, there's 4 occasions. I've got 4 y's for this person, so times 0, times 1, times 2, times 3. Okay, cool. Now I've got x. What's an x? X is a place that holds any predictors that have fixed effects. Fixed effects meaning intercept or slope. If you took a design of experiments with REL or anyone else, this is called a design matrix. It's where the predictors live. Predictors that have fixed effects in particular. In this model, which we have a fixed intercept and we have a fixed linear time slope, the intercept is the column of 1's. That's what we would have in any model to start us off with, letting the mean be different than 0. And then we have the value of the time variable that the slope is for next. So that's why it's 0, 1, 2, 3. If I had different occasions than someone else, my occasions would be here instead. Then we have this gamma matrix, which holds the fixed effects. Then we have this new thing called Z. Z is a holder for all of the predictors that have random effects. So we separate out predictors because you can have a fixed effect or you can have a fixed and random effect, and the latter shows up in here. At this point, because we only have a random intercept, Z has only the intercept in it. And therefore we only have one U for each person, U0, and here are the 4 E's for each person. So when you do the multiplication, you end up with this thing down here, which isn't quite so scary. I've got Y for each person is the fixed intercept, plus the effective time, plus the random intercept, plus the residual for that occasion. Okay, with me so far? Now, what does the model say the total predicted variances and covariances across occasions should look like? You've seen this before, but I hadn't given you the notation that goes along with it. V, the total marginal variance and covariance across occasions, is a function of G and R. We had that much before, but now I want to show you more specifically how that happens. Question from the audience. You cannot have a random effect without a fixed effect because a random effect is a deviation from the fixed. Yes. In order to have a random effect, you have to have the corresponding fixed effect. But the reverse is not true. In this case, we have a fixed effect of time without yet a corresponding random effect of time. So you can have more fixed effects than you have random effects, but if you have a random effect, you need a fixed effect to go with it. And I once had a student, by the way, from statistics, this was several jobs ago, say, nuh-uh, you can have a random effect without a fixed effect. I've done it before. I'm like, okay, you go ahead and try that. And she came back the next class kind of sheepish, and she's like, yeah, SAS wouldn't run. I'm like, yeah, I know, because you can't do that. It doesn't make sense conceptually, let's just put it that way, because random effects are phrased as deviations. It might be okay in the instance in which the fixed effect is 0 or close to it, to where the deviation part doesn't matter, but in general, if you have a random effect, the fixed effect goes along for the ride, even if it's not significant. But at this point, the only random effect we have is the intercept. So V, which is the total put back together again, is actually per person. This is super cool. I know you probably don't believe me yet, that having V per person is super cool, but it solves two problems this way. What if not everybody comes back for all the occasions? What if people don't cooperate? Well, then their V just has fewer dimensions. So if I have a study where people are supposed to be there for 4 occasions, then everybody should, in theory, have a 4x4 V matrix. But if somebody doesn't come back for the last occasion, okay, no biggie, their V is 3x3. Next. And what if people don't cooperate and they come back at times that are different? Their V matrix is going to be customized for them to adapt to that as well. But we're not there yet because V doesn't have time in it yet. So this is what it would look like for the V for a person who has 4 occasions. This is a random intercept, a column of ones. By pre and post multiplying G, it gets to be the right 4x4 dimension to be added to R, and then you end up with this V structure right here. So this is all a lot of notation to convey the idea that when you have a random intercept in the model, that is a compound symmetry model. A random intercept predicts the variance is the same across time, and it predicts that the covariance across time is only due to the random intercept, only due to person mean differences. That is what this model is saying. Okay, any of that you want to hear again or ask questions about? So let me tell you a quick story, if I may, because I sense the energy level coming down a little bit. So you have to be careful when you're talking about how the models that you use differ from models that have been used in your research area in the past. So I've been teaching longitudinal models and multi-level models for many years now, and students always get excited because they say, well, people in my field just do repeated measures ANOVA, and now I can do a multi-level model, and like I'll be cool. And I said, yes, you're going to be cool. So I had one such student who put a draft of a paper together, and he wanted me to look at it, make sure it was okay. And the introduction was, I'm going to go with the word sanctimonious. It was very much like, all you guys just did repeated measures ANOVA, but you didn't know about multi-level modeling, and I'm going to do that and be cooler than all y'all. And then you get to the model, and it's like, oh, well, I just had a random intercept, and then I did X, Y, Z. It's like, nope. If you just have a random intercept, what did I tell him? ... Can any of you guess? Was he cooler than everyone else who just did repeated measures ANOVA? He was not. Because a random intercept is repeated measures ANOVA. He might be cooler because he used maximum likelihood, and he didn't have to do listwise deletion because of that, but that would be the extent of the coolness. So it's imperative to recognize what is going on behind the scenes when you're making these sorts of decisions and what it actually says about the data. At this point, this is no different than an analysis of variance, because I haven't added any other ways that people get to differ from each other yet. That's coming. So intermediate summary, where we've done so far. We always start off with an empty model. An empty model has no predictors. Its sole purpose is to partition the total outcome variability into how much is level 2 between, how much is level 1 within. From that, you would get an intraclass correlation that describes the proportion of total variance that's at level 2. As long as that number is less than 1, play ball. That means you have at least some longitudinal variation. We could then get an estimate of what the trajectory looks like on average if we had balanced data by fitting what's known as a saturated means model. That is ANOVA. ANOVA treats time as a categorical predictor, which requires having balanced occasions that are the same across people and everybody coming at the exact same time. So everybody has the same possible set of occasions. If that is true, you can get the mean for each occasion and stare at it. Are the means flat? Are they going up? Are they going down? Are they going up in a linear way, or does it look a little bendy? The results of that saturated means model are helpful in guiding you towards which set of models is going to be most useful to you, because there's all kinds of ways of describing trajectories over time. So I think of this as the answer key with respect to what the fixed effects of time are going to be trying to do. A saturated means model in which each mean gets its own estimate is the right answer for what change over time is on average. It's not useful when you have more than, say, 3 or 4 occasions to talk about that as successive mean differences. Typically, people want to talk about a trajectory instead. And so that's where we go through and then start trying to figure out, okay, what kind of time model do we need? At this point, we only have one choice. The next unit is going to give you a whole bunch more. But if I have fixed linear time, that is a linear model, right? That's the 1 unit change, the change in y for a 1 unit change in time. It predicts constant change across people. So fixed linear time is something that I can do regardless of whether I have balanced data. So part of what I wanted to convey in showing you this here is that because this model operates at an individual level, each person gets their own predicted y. You can fill in whatever time values you want to across people, and the prediction is customized accordingly. So you can do this by treating time as a quantitative variable. Not everybody has to have the same set of times. So you don't have to have balanced data. You don't have to have complete data. You use whatever you got. In adding this fixed effect of time, we should be explaining level 1 residual variance. Part of the reason why the e's were deviating around the means is because the means were changing on average. Once we change the slope of the line, the e residuals should be reduced. So the fixed effect of time should explain level 1 e variance. In doing so, however, it's going to drive the level 2 random intercept variance up because of the implied correction factor going down. If we have only a random intercept, that is a compound symmetry model. That is constant variance over time, constant covariance over time. That is parallel slopes. That is univariate repeated measures ANOVA, just estimated with maximum likelihood or residual maximum likelihood instead of ordinary least squares. We always have a residual variance in the R matrix. We could add other things too, but if the reason why there's still dependency left over is because of individual time slopes, it's better to tackle that directly. So that's where we're headed next, is what happens when we're adding in a random linear effect of time that allows each person to get their own slope. Okay, are you ready to see it? Ta-da! So we're going to play Where's Waldo? Spot the new parameter. How does this differ from the other model? We found it. Yep. We have U1 right here. Whoop, there it is. That's what makes this different. So before we had a fixed linear time random intercept model. Now I am calling this a random time model. So by saying random, that includes the fixed effect already. It's presupposed. So if you say you have a random effect, that implies the fixed effect is there with it because of the aforementioned rules. But yeah, this is the catch. This U1 operates the same way as U0. It is a deviation from what is expected on average. So if people are growing on average, but you grow more than them, if you grow at a faster rate, your U1 will be positive. If you grow at a slower rate, your U1 will be negative. But U1 is the random slope deviation from the fixed slope. It is how far off. U1 is a variable. Gamma 10 is the constant. So the red is the fixed, the blue is the random. Together they work together and to create an individual slope for each person. And so that's what's shown down here in the composite notation. So each person's slope is a function of what's in common plus what is specific to them. And we are not adding a separate U parameter for each person. We are only adding its variance across people. So the term that gets estimated is the variance across people in these U1s. However, what we will also add simultaneously, even though it's not shown in this scalar notation, is a covariance between the U's. Because how far off you are from everybody else at the beginning should be allowed to relate to how fast you change. U0 and U1 are from the same person, so they should covary. They're both at level 2. So in adding a random time slope, this U1 term, we also add its covariance with U0. And if this is a lot, then I have a picture for you instead. So this is a picture that's also in the book. I did not realize that I ripped this off from Singer and Willett, 2003. This is in their book. I had totally forgotten that I absorbed that, and then I was flipping through their book a couple weeks ago and I was like, holy shit, I ripped this off. So yeah, this is their picture, and in the next version of my textbook, I'm going to properly attribute that. So my bad. So here is that model written out, and then I want to show you how the pieces work together. It was a good picture, to be fair, that's why I stole it. So the black line is the average trajectory for the sample, where these little black diamonds are the means on average at each occasion. The blue line is for a particular individual, where their triangles are the actual outcomes at each occasion. So if we start predicting each person's outcome, fixed intercept, what that is depends on how time is centered. So note the x-axis in my picture here where time starts at 0. So the intercept is always the expected outcome when the predictors are 0. Here that means time 0. So that means my fixed intercept is right here. And it is the end of the line. So the best of my PowerPoint drawing ability, it would be about 10. The line ends at 10. It's not the actual mean at time 0. It is the mean that is predicted by the model. So it is the initial part of the trajectory through the means that this linear time slope model implies. So gamma 0, 0 is 10. Now how do I get down to this blue person? Blue person started out lower than everybody else, no biggie. So their U would be -4. They have an intercept that is lower than the fixed intercept for the average, and so theirs is down here. So when you put those two together, you'd end up with their intercept of 6, which is where this blue line ends. Not their actual time 0 value, but the one that is predicted by their own individual trajectory. Giving each person their own intercept and their own slope gives them their own trajectory through their occasions. And so long as you've got more than 2, that line is not going to fit perfectly. So now these two work together to get us to where this person starts right here at 6. Okay, with me so far? Now we got to grow. Next stop, fixed slope. This is like rise over run in algebra terms. The change in y for a 1 unit change in x. So the average slope that generated these data is 6. That's the change in the y-axis for a 1 unit change in the x-axis. But my blue person here is growing faster than everybody else. So if I do their slope, their random slope is the deviation that gets them to what their slope actually is. So their change for a 1 unit change in time is 8. And so it's 6 that's in common, and then the 2, the positive 2, because they are growing faster than everybody else. So their slope in total would be 8 when you put these two together again. Then last but not least, E. E is what's left. So there in this picture, there would be 4 E's, although I didn't draw them all. E is the difference between what actually happened at each occasion and what the model said should happen according to their trajectory. So E is, why are you off your line today? Why is it that at time 3 you were lower than the trajectory thought you should be, but at time 2 you were higher? What happened at time 3? That's E. So E variance is, why are you off your line? Time-specific deviations at this point. So the overall variability in this outcome, according to this random time slope model, is now 3 things. 3 piles of variance, 3 variance components. 2 of them are at level 2. U0 is, why did you start out lower or higher than other people? U1 is, why did you change faster or slower than other people? Those are level 2. They live in the G matrix. The only way that they're going to be explained is by person characteristics. Then there's E, which is, why are you off your line today? What happened at that occasion? The only way to explain that is level 1 time varying predictors. So 3 different variance components in the model. We also have a covariance between the U's for the same person. So there's 4 things being estimated in the model for the variance in total. The variance of the U0 intercepts, the variance of the random slopes for time, their covariance, that's all in G, and then in R, the variance of the residuals, which at this point we're assuming is constant over time with no covariance. So 4 parameters in the model for the variance, only 2 parameters in the model for the means. Okay, how are we doing? Okay-ish? So that means that down the road, how many pseudo R squares would I be looking at? This is a finger question. How many kinds of variance does this model have in it at this point? Yeah, 3. U0 variance, U1 variance, and E variance. 3 different ways that observations differ from each other. 2 are people things, 1 is a time thing. Each of those can be explained. 3 pseudo R squares. Yep. Unbalanced time across persons, no problem. So what if you had a study where people were supposed to come in, say, at 3 weeks, 6 weeks, 9 weeks, and 12 weeks, trajectory should look like this. But then you had somebody who came in at the first occasion like they were supposed to. They came in at the second occasion like they were supposed to, and they never came back. Could happen. So what do? We use the 2 occasions that they do have. No biggie. I have somebody else who came in when they were supposed to the first time, but then they were sick when they were supposed to come back, and so their follow-up appointment was actually a little bit later, and then the same thing happened at their 3rd appointment, but then by the 4th one they were back on track. Okay, there's their trajectory to the best of my PowerPoint drawing ability. We use the occasions that they do have. So this person is unbalanced, but not incomplete. They have 4 occasions, they're just not the same 4 occasions as everyone else. But what if I didn't know that this was an option? What if the only thing that I knew how to do was repeated measures ANOVA, where time is a categorical predictor And so everybody has to share the same occasions. So if I took what was actually like week 7 and pretended that it was week 6, and I took what was actually week 10 and pretended that it was week 9, then the trajectory that I end up with is wrong. So this is to say, do not round time into convenient intervals when fitting these models. You don't have to, and it's a bad idea. You can do that just to make a picture. So like if I just wanted to get like a saturated means model where everybody had slightly different versions of time, I could round to some convenient interval, nearest day, nearest week or something, just to make a picture to get a sense of what I was looking at. I would not use that in a model though. So we can use whatever time values each person has in estimating the random time slope, and we can use as many values as possible. If we were to try and estimate each person's individual predicted trajectory though, the one for this person down here is going to be biased. Anybody who has fewer occasions or whose trajectories look way more discrepant than everyone else's, if you actually go to the trouble of predicting their individual trajectory from the model, it's not going to match. It's going to get pushed to the mean. And the term for this is shrinkage. And it happens because these U's that we're talking about, these random effects, these are factor scores. So when you try to make observed realizations of them, they get pushed towards the mean. So you don't want to do that. The beauty of these models is that you don't ever have to know what the U0 or the U1 is for anybody. You can just predict the variability across people to answer research questions about why some people start out higher and why some people change faster. You don't need the U's. The U's are really more of just an idea rather than a quantity. Their variance across people is what gets estimated. So here's a summary then of where we've gone so far. Empty model, fixed linear time model, random linear time model. So the difference between the first one and the second is right here, adding one fixed effect that allows some kind of change over time on average. The difference between the second one and the third one is this typo. Ugh. Why am I yelling at my screen? What did I do? Let's turn this into a pedagogical exercise. What's wrong where my pink mouse is pointing? Oh yeah, it should be a 1 there, not a 0. I believe that is a copy-paste error, so I will fix that and repost the slides. I hate it when I see that. You know what's interesting to me is that like I've probably used this slide 8 times. So either I like forgot to fix it or I never noticed it. But it does need to be a 1 there, not a 0. All right. I'm thinking, yeah, let's do this part and then we'll call it a day. I think this will be the next thing here. So this process of trying to figure out which terms in the model each person needs their own of is what's actually happening when people say that multi-level models handle dependency. So you know how I feel about the word handle, right? Handle is what people say when they don't know what they're talking about. Missing data is handled. Dependency is handled. It's just handled. Like, I don't want to know what happened. Just fix it. All right? Handled. I want you to know what happens. So the idea of handling dependency requires us to understand what is dependency in the first place and where does it come from. The word dependency means correlation. It's the idea that residuals, so the E's from the same person, are going to be correlated. The reason is why. We have to figure out a way to tell the model why we think that is to be able to predict the correlation amongst the E's. So there are 3 reasons why we might see dependency in longitudinal data. There's probably more, but these are the 3 that we're focusing on. So we did number 3 last week. Non-constant within-person correlation for unknown reasons. That's what the R structure models are for. the autoregressives and the topolitzes and other things like that that allow residuals that are closer together in time to have a correlation. Cool. The first two is what we're focusing on now. So other sources of dependency, one is constant across time and one is not. The constant source of dependency is the idea of person mean differences. Some people start out higher or lower and they stay that way. That induces a correlation between their E's. That's what a random intercept is included for, to predict a constant correlation of the residuals from the same person across time. The one that we're adding this week is right here. Another reason why E's from the same person can be correlated above and beyond just mean differences is people having different slopes. So what we're talking about right now is a slope for time. The idea that people change differently from each other. Some people change faster, some people change slower. That in turn induces another kind of dependency. It also induces heterogeneity of variance because as people grow differently, they spread out. So that's another source of dependency. But I am being deliberately more general here to set up the idea that any variable that is measured repeatedly over time can have a random slope. So if I were to measure, say, stress and health over time, I could have an individually varying relationship between stress and health. It would be the extent to which, if you're more stressed than usual, you feel crappier than usual. The tie between stress and health could vary across persons. That's a more general idea of a random slope that applies to any level 1 predictor, not just time. It's a source of dependency. But this is what random slopes are for, is to capture the heterogeneity of variance and covariance that results as a function of that predictor. So here's a schematic that's in the book. I don't think I stole this from anyone. I think this is mine, but I could be wrong. This is where the idea of piles of variance for the name of the book's website came from, because this is the way that I make sense of these things. You know, once upon a time, we talked about all of the variability in an outcome as one idea, as E variance. The first thing that we did in this class was to split it into two piles. What is level 1 E within person variance, and what is level 2 between person variance in the random intercept. So then we have a proportion out of these two circles. How much of it is the lower one? That's your intraclass correlation. So if I focus on this circle right here, this is my E variance. It's why are you off your line? Why are there deviations around your person mean? Well, maybe it's because you're changing over time, in which case the line that's given by a mean that's flat doesn't fit. If you're going up or you're going down, that's going to cause additional E variation. We are going to capture that by splitting this variance component into these two. So what we used to just call within person variation over time at level 1 is now two different things. Part of what was within person variation is the idea that some people change faster than others. That's my level 2 random linear time slope variance right here. So there was actually another between person buried in it. And we know that it is because we can test it as a hypothesis and see whether or not we have evidence to say that, yeah, people need their own slopes and that this needs to be pulled out of here. After we give each person their own linear time slope, their own trajectory, there's still E variance left as why are you off your line? Why are you higher than you're predicted at this occasion but lower than predicted at that occasion? And so where we are now is this idea that all of the dependency in longitudinal data that is being handled, it's being handled by these two circles right here. It's being handled by saying some people are higher or lower than others, that's my random intercept. Some people change faster or slower, that's my random time slope. Because these are both people things, they get a covariance, but then E is what's left. But we might need to pull some more stuff out of here. One of the reasons why you might be off your line is that maybe you need a bendy line. Maybe a straight line is not good for you. Maybe you need a bend, like a quadratic effective time or an exponential effective time, something like that. If we need some other variable to capture a non-linear change, then we can pull a third circle out of here and say that people need their own non-linear change as well. So then that would induce a third kind of dependency that's being predicted for the variable. So this is to say, handling dependency happens through random effects. Your job is to figure out what all random effects need to be in the model to handle that dependency. All the sources of correlation of the residuals from the same person. So the process of multi-level modeling is just pulling piles out of this residual for as long as it takes. So we can pull time-varying predictor slopes out of here as well, and that would be like a fourth level 2 pile. So, all the fun that you can have with this. This is the idea, though, of what people say when they mean handling dependency. It's through random effects. And if there's correlation over time in the residuals that's not due to random effects, you can put that in your model too. So in studies in which you have a lot of occasions, for example, you might have a random intercept, a random time slope, and an AR1 correlation in the residuals that are left. That might be necessary in such cases. So you have a suite of options for how you can specify a predicted correlation of occasions from the same person. All right, questions? So this is the idea of piles of variance. Random effect piles are level 2 piles. They get predicted by things that vary between persons only. Level 1 piles are within person piles. They get predicted by time-varying predictors. And anytime that we add a fixed effect, we're explaining variance. Every time that we have a random effect added, we're making a new pile. So this is a very important distinction to have conceptually as to what's happening. If I say that each person needs their own slope, that's still an error term. I don't know why they need their own slope. It is an unexplained phenomenon. I just know that they need their own slope. So I don't think it's appropriate to talk about explained variance due to random effects because you're just partitioning out error into different places. Only fixed effects explain variance with known predictors that are measured in your sample. And for those of you who are from, let's say, sociology, econometrics, political science, and other places that do fixed effects models, this one's for you. You could have fixed effect for people instead of random effects, but then you couldn't predict why people differ from each other because you have saturated the model by putting in person ID as a predictor. So it does control for dependency, but it does so in a way that's super unhelpful. So, happy to talk more about that next time because we're out of time. So any questions before we adjourn? All right, then office hours start now. Have a great weekend. Please do your next formative assessment, and I'll see you next week. Bye, everybody. Thanks for joining us.